Yes, indeed. In fact, so this is a draft copy of the book, which I was planning on passing around, so that whenever you have a question, you can first check in the book whether you see the answer. No, hold on. It was for some other purpose. I forgot. Okay. Since I got the question during the break, I think it's useful to not skip over this example of the bouncing ball, which is the most impoverished type of physical system you've ever heard of, but it happens to be a hybrid system. So, of course, its dynamics is follow this differential equation. Height changes with velocity. Velocity changes with minus gravity while the position is above ground. And ground is very visible here at height 0. And then after this continuous dynamics, which can evolve for any amount of time, including too short, you check discretely whether you happen to be on the ground. If you are on the ground at height 0, then you change the velocity around to be minus some damping coefficient times velocity, and you repeat the whole thing any number of times. And so here's a typical trajectory of what bouncing balls might do. But in your time as a child, which you have been, no doubt, I'm sure you've experienced a lot more behavior of bouncing balls. But if you look at it from our new and improved multidynamical systems perspective of, I say, well, that's the motion, all right, but in fact, it should be a composition of simple continuous dynamics and simple discrete dynamics. Maybe a slightly better picture is if we put our multidynamical systems spectacles on, we'll see that the actual behavior is maybe better depicted like this, that we have a continuous time axis and a discrete time axis. So time becomes two-dimensional, say. It's not in the semantics, it's not so important, but it's useful as an illustration device occasionally. And then here's the continuous evolution, which is just continuous, very simple, which evolves for a certain period of time. Then we do a discrete computation where we check velocity and we invert it, and then we follow another continuous evolution for a certain period of time. And then we happen to have hit the ground. We do things discretely, like changing direction and velocity around, and another continues and discrete and continues and discrete and continues and discrete. And so the two projections are a lot easier to understand than the original one. Just mind you that hybrid systems do give you a bit of a funny notion of time. This is what happens when I plot the time coordinate on the bottom of this plot in a separate axis. And if this is what time looks like, this is a little funny. And that's also the reason why I don't do with any explicit notions of time, because it just is a complication of what's going on. It's a lot easier to understand everything from a pure logic and programming languages perspective, where everything is defined compositionally right from the get-go. But sometimes this picture helps a little bit. And okay, there's other examples that you can go through, but you can go through them on the slide. What I really wanted to do is now switch gears and move away from modeling cyber-physical systems and asking questions about them and specifying what they're supposed to do, and move into, well, that's great, but how do we prove that that's the case? Because I started out saying that real cyber-physical systems are so important to us that they do deserve proofs as safety evidence. Let's go for proofs. These are the proof rules. These are equations of truth. They basically equate one true fact with another true fact. But I think it's easier to understand them, again, one at a time, as opposed to, even though they do happen to all fit on the slide, understand them one at a time. So for example, if we're trying to prove that after a discrete assignment, if I put the expression E into the variable x, P is true of x, then how can I rephrase that logically without mentioning assignment again? In a picture, if I change state from here to the new state, where I went by assignment, and I want P of x to be true over here, what do I need to be true over here to imply that P of x will be true here? Any takers for that question? I have to be? I have to prove P of E, right? So in other words, this guy is equivalent to P of E, right? And it's a pure syntactic transformation to go from left to right or right to left. They're equivalent, they're easy, just discrete dynamics. Just discrete dynamics is really easy. Okay, differential equations, well, not so much. But at least it's just a differential equation. There's no hybridness in it. There's just always along a differential equation, P is true of x. So no matter where I go, by evolving continuously, P is true of x. How can I rephrase that in the most obvious way? By working with the What did you learn in, okay, let's say not high school. What did you learn in college? The reflex for a differential equation is somebody hands you a differential equation and you go ahead and solve this darn thing. Okay, let's suppose we went ahead and solved this darn thing. Y of t is the solution for it, so as a function of t, obviously, time. So if we now assign y of t into the variable x and then show that p of x is true, we have obviously shown something about the solution. But have we shown all we need to show? Because we're missing?
Well, t.
What's t? Right. This is talking about always along the differential equation p of x holds true. And here we say, well, at time t, if I assign the solution y of t into variable x, then p is true of x. That's not enough. So I need to make up for that, of course, by saying for all times t greater or equal 0, blah, blah, blah holds true. Right? So very easy. If we instead have an evolution domain constraint and q of x, then things get a little more complicated. They're not just that, but I have to say, for all times this is true if, for all intermediate times the evolution domain constraint was true. So in other words, for all times t, if for all intermediate times s, the evolution domain constraint q is true for the solution y at time s, then after I assign the new value y of t solution at time t into variable x, p is true of x. Yeah? Very easy. Yeah. Caveat, I need solvable differential equations. If you're curious what I do without solvable differential equations, wait until the next lecture. For now, we'll only talk about elementary cyber-physical systems, the ones that have a lot of challenges, but not in their continuous dynamics. Test. This is probably the most subtle one, but it's actually easy. So if I want to show that always after running the test whether q is true, I want to show that p is true. How could I do that? Q implies p, right? Because always after running a test, well, the test only runs if q is true. So I guess what I need to show is that q implies p. Also easy, right? These are all equivalences. The most expressive form of reasoning we could possibly have.
Can I ask a question?
Yes.
In the first two, instead of a generic formula, there is just a predicate. Is that
Yeah, right.
because there are some issues or
No. But I am prefetching something that I won't actually have time to talk about, but it's in the book that's running around. Also in the Journal of Automated Reasoning article. Whenever you do assignment, the way we do this for real is that whenever you substitute, what do you have to pay attention to? Bound variables, clashes, captures of variables, that sort of stuff. So, yeah, easiest thing in the world, sure, fine, but you have to be a little careful and so on. And the best way to make that happen without having to worry about what on earth happens with substitutions, captures of variables, oops, soundness clashes, all of the map and the whole reasoning, is to solve the problem once. And that we do that in the uniform substitution algorithm, which excels at this question of what can I put where and when. And then the rest of the day, I literally implement this axiom by copy-paste. I literally implement this axiom by copy-pasting this particular differential linear logic formula, in which indeed p is a predicate symbol of one argument, and then p of x is what I have here, and p of expression e is what I have here. And I just copy-paste this formula and then uniformly substitute in whatever the hell I want concretely and so on. And that's why something that I'm not emphasizing, I have slightly different notation in all kinds of places, because it is already prepared for that sort of thing. But don't you worry about that too much. That's what's really happening here. Okay. So don't forget, we have a compositional semantics which enables us to do compositional proofs. So the rest of the game should work compositionally. Now we have discrete, continuous, tests iron out. These are the atomic operators in the programming language. The rest should do the composing operators, the ones that combine them. But let's do them in the compositional style, please. So for example, if we would like to understand whether always after a non-deterministic choice to run alpha or beta, some postcondition P is true in a picture always, no matter whether I run alpha choice beta by having run alpha or by run beta, I always want P to be true. How do I show that in logic? that P is always true, no matter what happens with alpha choice beta.
Conjunction.
Of what?
Alpha, P, and beta.
Precisely, right? So we need to show that all alpha runs are safe. That's what this subformula does. And we need to independently show that all beta runs are safe, which is what this logical formula does. And then the conjunction of the two expresses that indeed all alpha runs are safe and all beta runs are safe, and actually alpha choice beta doesn't have any runs other than those that come from either alpha or from beta. Yeah? So the two are equivalent, and I'm done. And it's, again, very important that this was compositional, because what did we do? We said, here is one formula about a slightly more complex program, a program that has a choice between alpha and beta. And we reduce it to a long list of conjunctions, okay, fine, but of individually simpler formulas. This is just a question about the subprogram alpha that has one operator less. This is just a sub-question about the subprogram beta, one operator less. I can, take operators away only finitely often from a finite size program. And then at the end of the day, I must have been at one of the atomic guys, either discrete or continuous, and they're simpler, multidimensional systems principle, right? So and then we're done. Okay.
Is that an axiom? It seems to
Yes, and this is an axiom indeed.
It seems derivable
From what?
from the previous characterization that box QP is Q implies P.
From this guy?
Yeah.
No. Because test whether Q is true, that's a test on the logical formula Q, right? So you're testing whether logical formula Q, such as velocity is greater equal 0 and distance to the other car is divisible by 29, or I don't know, some nonsense. Huh? You're just testing whether that formula is true, and then this is equivalent to this condition you're testing implies that. But that's a very fundamentally different operation than, allowing a choice to act and change. Tests never change state. They only impose conditions on the state and filter. They're a filtering device, ultimately, really. Yeah. But this guy changes state. It changes state by either running the alpha program, which can contain assignments and differential equations and tests and repetitions and any number of them, and so does beta, right? So it actually acts and does stuff. It is not derivable. It's very fundamental. Of course, we can justify it very easily from the semantics. We can just do a soundness proof for this axiom and justify that this axiom wasn't written down for naught, but it makes a lot of sense. But it's a very simple calculation to prove this axiom sound. And indeed, this is useful by and large, that each of our axioms is a simple soundness justification, and then the proof is just a long list of all these equivalences used. I'm using equivalence 1, equivalence 5, equivalence 7, equivalence 29, or something like that. And that's the end of the proof. Very easy. Right? And that's super useful because it enables us to do gigantically complicated systems from extremely simple sound ways, in fact. So sound that we prove them sound in Isabelle and Koch, and have them in our own Chimera X theorem prover as well. Okay. Sequential composition is the next guy to worry about. We want to logically reduce the question, always after first running alpha and then running beta, are we safe? So always after running alpha, then beta, over here we're safe. Or over here we've come through some intermediate state by first running alpha and then running beta. How can we logically rephrase this in simpler ways?
There exists an S such that if you run alpha, you get to S.
Uh-huh.
If you run beta from S, you get to beta.
That would work, except exists an S is a bit of an idiotic thing, because how big is S is the question in a certain sense. It's a full state. So the full state is going to be characterized by some finite number of variables, because we're living in a finite dimensional vector space. But still, I have, like in a 20-dimensional system, I would then have 20 quantifiers. So it is correct, but makes our reasoning unnecessarily complicated. For that reason, we say something like that, but in easier ways. Because what is it that I wish would be true at this state S? I wish that it would be true that beta box P, right? All beta runs will be safe. So how do I say that this is true not just here, but after any alpha run?
Another box.
Precisely. Alpha box, beta box. So I'll say, over here I want all beta runs to be safe, which means over here I want to be true for all alpha runs that this thing is true. that all beta runs are safe. In other words, we have the axiom that says after all runs of first alpha then beta we're safe, if and only if after all alpha runs it is the case that this guy is true, which means that after all beta runs we're safe. This is the most deceptively simple axiom you've ever seen. Of course, using this as a piece of cake, all I do is erase the semicolon and replace it by more square brackets. That's a piece of cake, right? So using it in our reasoning, that's super straightforward, right? But justifying why is that okay and so on, and how is that fine, and how is this a reduction and so on, that's a little more subtle, right? It is a reduction because, again, the size of the programs all went down, right? Here's a program with one more operator, alpha, semicolon, beta, and here we've got subformulas that only talk about pieces. The post condition went up a little bit, but individually they're simpler. If I keep on decomposing, someday soon I'll be done. In fact, if you compare this guy, I'm not sure who here has ever seen Floyd-Hoare calculus or Hoare calculus, right? Okay, so the sequential composition guy in Hoare calculus, for those of you who haven't seen that, just don't listen to me. But for those of you who have seen that, the composition rule in Floyd-Hoare calculus says if you find a sequential composition, dream up an intermediate condition. There we go again in a certain sense. We dream up something creative, some logical formula describing what on earth could be true always after running alpha. So you're trying to characterize this as a logical formula, such that what we know then is good enough to imply that all beta runs are safe. But all of a sudden we need to be very creative in dreaming up this intermediate condition. So every sequential composition we say, I wish I wouldn't have to do that reasoning now. I have to become creative and write down a whole bunch of more formulas. Here we don't have to be creative. The formula that perfectly says what is true always after running alpha, and which very definitely implies that all beta runs are safe, is very much the syntactic formula all beta runs are safe. Beta box P, piece of cake. Right? So just a sequential composition turns into a very simple syntactic transformation. But, yeah, deceptively simple. Leaves us only with repetition. What on earth do we do with repetition? I want to follow the same paradigm. I want to rephrase equivalently that all runs of repeating alpha are safe, that no matter how far we go by having a repeated alpha, we're always safe. How can I rephrase anything here? Well, let's start easier. What has to be true right now if we want to make sure that all repetitions of alpha are safe? P should really hold right now, otherwise we're in deep trouble. Yeah? What else should hold?
After alpha, again, this one.
And precisely, after all alpha runs, we want all repetitions of alpha to be fine, right? So this is equivalent to P holds true right now, otherwise we're lost. And after all alpha runs, so no matter how far we go with running alpha once, alpha star P is true, that no matter how often we repeat alpha, we will still end up at a safe state. In other words, this axiom says that repeating alpha will be safe if we're safe after 0 iterations or at least 1 iteration. That's another way to read that. We're repeating alpha at least once. Yeah? Okay, it's an equivalence. This is beautiful. Equivalences make us happy. What's the catch?
It's not a reduction.
I have to argue a lot in why and in what way this could ever possibly constitute a reduction. Actually, it's a very subtle way of arguing that case regardless, but it really isn't easy to see. And it depends on a lot of circumstances. The point is that if we just do that, now we say all we need to do to prove a property of repetition is to do some stuff and then prove a property of a repetition. Shoot, isn't that where we've been at a moment ago? So not a whole lot of progress. So let's start over. I want another characterization of repetition. This one is cracked sound. We use it occasionally, but it doesn't do everything it ought to. The other way of doing it is we still want P. Now that we have P, what do we need to get P next time? That P implies alpha P, right? If I had that P implies alpha P because I already have P, I would also have P over here. Right? Do I also have P over here? No. But almost. We get that when we say we want P, and after any number of iterations of alpha, we want that P implies alpha P. So in other words, here we've got P, and since 0 iterations of alpha are permitted, we do have that P implies alpha P right here. Hey, we've got P, so next time we have P, right? Next time we've got P. But hey, the repetition is also allowed to run once. I've heard of that, repeating loops once. So if P, then alpha P also holds over here. Hey, we've got P. That's awesome. So I guess next time we really got a P. So we have a P fact over here, but repetition can go twice, which means P implies alpha P is true here as well. We have the fact of the postcondition P is true right here. So I guess next time around we also have the postcondition P, and so on and so on and so on any number of times. Yeah. This is the actual way of doing induction. Yeah. Okay. Usually the way you've seen induction probably is more like that, that if you would like to prove a property of a repetition, that you go and dream up a loop invariant, J, that you prove is true in the beginning. So you prove that out of your current knowledge, gamma, for example. And you prove that your loop invariant actually is a loop invariant, meaning it continues to be true for the loop. So if you run the loop body once, then if the loop invariant was true before, then it's also true after. And you prove that it was good enough to actually imply the condition you were interested in the end, so that it implies the postcondition at the end. You've probably seen it in this form more. Yeah? It's easily derivable out of what I just showed you, because you can say, out of this guy, by a cut, you can show that cut or a lemma or case splitting or anything you want. You can show that, I guess if I show that J, then I get to assume J, right? That sounds easy enough. That's a cut. If I show this guy, then I assume this guy. That's also easy enough. So these are just two cuts that I've used here. Show a lemma J, use a lemma J. Show this lemma, use it, right? Over here, we now show the property of a loop by expanding it with the induction axiom. Let's just replace the left-hand side by the right-hand side. Right, from here to there. Easy. This guy, J implies J, that should be easy. And some other stuff. So I guess what I need to show is that J implies this other stuff. And one way of showing that is by the generalization rule, that if we prove the postcondition is true, valid, no matter what, then it also is true. If P is true, then it's also true after running alpha. Of course, right? So we do that here, and we show that because this thing is true, that J implies all runs of alpha satisfy J, then it's also true after running alpha star. But this is possibly a bit of a loss of information, but it's always sound. Likewise over here, by monotonicity principle, if we show that P implies Q, we've also shown that after all runs of alpha, P implies that after all runs of alpha, Q. We use that here to show that since we have alpha star J, so after all runs of repetition, the loop invariant holds, then also the postcondition holds, because the loop invariant does imply the postcondition, piece of cake. And it also does inform us that, of course, finding a loop invariant can occasionally be a challenge, which is an understatement. We've got invariant generation techniques, but they don't always work. But it does inform you also what the loop invariant needs to do. It basically needs to carry around what loss of information you suffered by having deleted the alpha star, which means you basically need to carry around whatever information from the past runs of alpha you still need for this property to be true, because it was an equivalence, so it characterizes exactly what you need to know. You just need to rephrase it a little bit in other kinds of logic. Yeah. Good. Okay.
So one question. So
yes.
So I'm wondering how the rule G is justified, because maybe some statement will change the value of the variable.
Mm-hmm.
Yeah.
Yeah.
So
this is Gödel's generalization rule. If P is valid, then it's also valid after all runs of alpha. So if P is valid, P has a proof. If things in a sound proof system only have proofs if they're true under all circumstances. If P is true under all circumstances, it also must be true after all runs of alpha. So if you have a proof of P, you also have a proof of after all runs of alpha P. This is not the case for diamond. This rule does not hold for diamond, because for diamond it could happen that even if P has a proof, so it's true under all circumstances, that doesn't mean there is a way of running alpha to a state where PL is true, because maybe there is no way of running alpha, period, because it has all kinds of contradictory conditions and so on. But for Box, it is true. That's Gödel's generalization rule from 1940-something. He didn't phrase that for differential atomic logic, but in a simpler modal context, he phrased that. Good question. Okay, so the lion's share of understanding comes from understanding what does change and what does not change, because invariants are a fundamental force of computer science. These guys that we now need to find for loops, things that don't change when our system evolves, is the most important task in computer science. And also variants, so things that do tell us what does change, are the most important part of computer science for liveness properties, for when we want to make progress toward a goal. We don't need to find just what doesn't change. We need to also find, hey, but this does change. Maybe our distance to the goal changes. And how exactly that changes depends a little bit on the model in question and so on. These are the two most important questions, and indeed you can show that these are the only questions in town for cyber-physical systems. Okay, but now let's use this thing. We have a car, and one part of the car is going to be the case where the car brakes. In other words, the acceleration goes to minus b for braking, and then we follow the differential equation. And at the end of the day, we would like to make sure that our position is less than the stoplight position. Yeah? And at the beginning, at least, we should be assuming that our position is less than the stoplight position, because if we're not even assuming a post condition, we're toast. Yeah? So that's one of the cases in the proof that we will want to do, and usually it's a good strategy for doing proofs if we first exploit compositionality and look at one part of the system, figure out a proof of that, and reassemble it together. Not the only way of doing it, obviously, but I like that style because I have to squeeze less on my slide. And then, just to make sure I've said that, gamma turnstile delta, that's the shape of the conjectures that we're proving, for example, like that one down here. And on the left-hand side, we gather all the assumptions. On the right-hand side, in the sequent, we gather, the things we would like to prove, which are read as a disjunction of all the facts on the right-hand side. Anything in this disjunction is fine. And then we start with the conjecture at the bottom, the thing we would like to prove, and reduce it all the way to the top. And how we do that is simply by using the equivalences I've shown you. Selectively pointing at a position and saying, dear formula, please replace yourself with whatever you're equivalent to. So a proof is a bunch of pointing, and then we're done.
So excuse me?
Yes?
I'm not sure I understand all notation. When you have this symbol like T...
the turnstile guy?
So it's the same as an arrow, or is it...
It's really, the meaning is really an implication. The only difference is, the only formal difference is that this guy means the conjunction of all the list of formulas, or on the left-hand side, implies the disjunction of all the list of formulas on the right-hand side. But really, the turnstile is an implication.
So why don't you put an arrow?
Well, that has formal reasons only. There is no good reason for it.
No good.
There's no really good reason
And
for it.
what is the bar?
The problem is if I put an implication, people confuse the implication with the sequent arrow and think that you can write a comma on the left-hand side of an implication, which you can't. So it's really just a formal reason.
Okay.
There's no strong reason for it. Okay. And also the fact that you develop proofs from the bottom to the top. Yeah, stupid. But historical precedence. Huh? It has a deeper reason too. I'll get to that in a second. Okay. Now we have this fact at the bottom that I would love to prove. Yeah? All I need to do now is point at this sequential composition and say, let's use the sequential composition axiom that replaces the semicolon by more square brackets, right? So we use that here. We point it at the red fact and replace the left-hand side of the axiom with the right-hand side of the axiom and say, well, I guess our sub-question is whether after all runs of this, it is the case that after all runs of that, blah something. Yeah? Okay. Next thing, I point at the assignment and say, dear assignment, please replace yourself with the right-hand side of the equivalence. Which means, because that's the place where the A is, that we write minus B instead of it. Yeah? So in other words, we put the right-hand side of the assignment in for the left-hand side. That's easy, actually. Okay, now we have a differential equation, but fortunately it's an easy one, so we can solve it and say for all times t, if x is changed to the solution of the differential equation as a function of time, our post-conditional is true. The assignment, again, we can put in. We can point to the assignment into the middle of the mix and put in the new value of x in place of x, and then simultaneously expand the definition. Right? It was x less or equal m for now. And so this is the question that we have. And now we're sort of stuck in a certain sense because all the programs went away. That's a good thing, right? If all the programs went away, because that means we now reduced it to just a question of the simpler arithmetic. The simpler arithmetic here is real arithmetic, which has, ever since Tarski, the beautiful property of being decidable, which is a bit of a shock. So there's an algorithm which, for any real arithmetic question like that, will tell you in finite time whether it's true or false. I'm not sure if you can believe it, but it happens to be true. A miracle of Tarski. Sad fact of life, the complexity isn't awesome. Yeah? So, but here it's not so bad. So you say arithmetic, please prove this. And will it come back with a yes? It shouldn't, because even if we start at before the stoplight, if we brake, we won't stay before the stoplight if our velocity was bad, right? So of course it has to come back with a no, but it comes back with a better version of no. It comes back with a condition that says, well, actually no, but if only this would be true, I would have said yes. Yeah? Because Tarski's quantitative elimination also gives you equivalent reduction. So here it comes back with, well, all right, if the velocity isn't too high, phrase like that, or some logical rephrasing of it, then I could prove this. And so what do? We say, I guess we cannot prove this, except if we knew this. And it makes some sense, because this sort of characterizes the braking curve of the system, right? Velocity changes. If we don't want to exceed the stoplight, I guess if we're far enough away, we can tolerate a lot of velocity, but if we're getting closer, velocity has to drop. Okay, so we use this as the new version of the loop invariant, new guess for it, and yeah, indeed, that case will work. It's now proved, because this is then our assumption, and we have a proof. And this is how, developing it from the bottom to the top, if this turns out to be true, then because it would sound, this implies that, implies that, implies that, implies that, implies that. This is the thing we wanted to prove. Likewise, the acceleration mode of the system. You'll say, well, my system is safe if I'm accelerating, and you keep on doing the same principle and so on. Apply the point to places and apply axioms is all pretty easy peasy. Except you do get out a new condition from that, because it is also not always safe to accelerate. Sometimes you have to be more cautious and brake. And so you will get a condition out of it which basically says how you have to choose your start braking condition that I haven't told you about. This is how. Well, this is the condition. So if this has to be true for all times between 0 and epsilon, I guess this has to be true for all times between 0 and epsilon. In particular, it has to be true for t equals epsilon. And as soon as it is true for t equals epsilon, it's true for all the intermediate points in time as well. So that's how that sort of thing is constructed. And there's a proof, which basically intuitively says, if I'm speeding up still, then because I might be speeding up for a certain reaction time period, I have to respect the fact that I traveled space and my velocity increased to make sure that I can still brake. And if this curve doesn't fit into the safety envelope, I have to start braking right now. And then, if you have the whole system, which can either brake or accelerate, then out of the thing we just constructed, we have a proof, because the loop will simply be proved by finding a loop invariant. Hey, we just synthesized that. Yeah? And then you prove brakes into exactly the braking case and the acceleration case that I showed you on the slides. And you're done. Notice the proof is follow your nose. It synthesized the loop invariant and the parameter constraint and the go and some other goodies. And it is indeed often effective to first look at pieces of the proof before we look at other things. Let's go back and yes.
So you have a strategy now for constructing the loop invariant. Do you have an idea for which class of system this is?
In a certain sense, we can't, because you can show that the only hard questions in town are finding loop invariants. The calculus is complete. I hope I'll get to that. In fact, since you raised the question, let me get to that right now. Let me not get to it right now. Let me first show you how you do it. For example, in the bouncing ball case, this is the Chimera X theorem prover, which mechanizes what I've just shown you. I hope the font size is sort of reasonable, right? what it says is here's the differential equation that I've shown you on the slide already. Gravity is acting on it, and here's either if we're on the ground and we invert velocity, if we're not on the ground and we don't invert velocity, and then prove that you're always above the ground and below the initial height.
So you're blocking the...
Oh, I'm sorry. I will sit down and then I will be out of the way, I hope. If not, please let me know. Better? Yes. Okay. Okay, and then you can either prove it sort of with a tactic. In fact, the tactic auto would have done it too, but it's not interesting to show you the auto tactic. Or you can start conducting a proof with it in which you basically point to facts and say, please act on this fact. So this proof rule has just pushed all the assumptions on the left-hand side. Here's all the assumptions. And for example, I could have done split a conjunction. If I assume a conjunction P and Q, I can just as well just assume P and Q separately. Right, so I can use that guy. Yeah. Click on it. Or I can act on the loop. And then loop, it will tell me, well, what you need to find is this blue dotted formula here, which holds true in the beginning, which, if it is true, after running the loop body just once, it is true again, and which, if it is true, implies the post condition. And then, of course, I could start, this comes from somewhere, and I could start editing in here and so on. It would change the other ones too, and say, okay, I want to run this loop in their end. Here, this is just arithmetic. You know? So we would say, please use the pocket calculator of quantifiable elimination and do the arithmetic for me. This is the is it safe at the end case. It's also just arithmetic. And this is the actual interesting inductive case. We say now that the loop has gone, no more loop in it, we want to show that if the loop invariant is true, then after running the loop body once, the loop invariant is true again. And we would say, well, I guess we would use a sequential composition axiom that after running A, semicolon B, we're safe, if and only if after running A, it is the case that after running B, we're safe. So let's click on that, which of course is the default if I just simply click on the formula. The idea is always I point at the formula and it will do the thing I happen to want with it. Or here at the end, I just show you the axiom because then I can remind you what's going to happen. Here we use the choice axiom that says in the middle of some formula, even after the ODE, I just leave the ODE in place. I could be handling it, but I can also just leave it in place. I want to show that after all runs of a system that has a choice to either do A or B, I'm safe. If and only if after all A runs, I'm safe, and after all B runs, I'm safe. Concretely, that means after the ground hit us, we're safe, and if the ground didn't hit us, we're safe. So let's click on that. Sequential composition again. Yeah. Let's click on that. And of course, I can also, mind you, it is synthesizing a tactic for me as I'm pointing at facts, which is first useful to replay exactly the proof that I've just done, but also useful to learn how you can write tactics by observing what the system is doing that do the same thing without you having to do anything, where you just say, okay, unfold everything in the usual obvious way and show me the interesting parts. In fact, because that happens to be helpful so often, we also have a bunch of buttons on the top to unfold to the interesting places, basically. But you wouldn't learn anything if I just push the auto button, so that's the reason why I'm not doing that. So here I point at an assignment, for example, again in the middle of a formula. And I can look at, for example, wait, what did it do? Here it points to I acted on this assignment and changed it around. Or here, for example, I acted on this semicolon and changed it around. Or here I acted on this choice and changed it around. So you can sort of trace the proof and see what's going on. Up here, the test, of course, turns into an implication. So let's do exactly that. This test also, if I just click on it, turns into an implication. And now what I happen to have done is I've changed the post condition, which used to involve some programs, into something that's program free, just straight out arithmetic. And now I can handle the differential equation, which I also could have done earlier, but I think it's a little bit easier to see if I do it like that. And then I can either solve the ODE or just use some automatic tactic that says, okay, well, never mind, here's an ODE, go and have fun with it and try and prove it. In fact, solving the differential equations is also, of course, you shouldn't call an ODE solver and just believe the answer, because they lie most of the times. So instead, we construct the solution and then prove that the solution actually is a solution as part of the proof, which is why solving ODEs actually takes time. Because, well, you do the solution and then you say, ah, shit, why is the solution a solution? Proof, 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 proof. It is one. Great. I can go back to this later on. Now you have a proof of it and can download the tactic and so on. Okay, that was the proof of the bouncing ball thing. In similar ways, can you prove, for example, this system where you have a robot that's moving around and is moving around on Dubin's dynamics paths, so on circles and line segments and so on. And if there's an obstacle somewhere, of course, there's some conditions of, if these are the differential equations for the robot, which describe this motion in the space, and the system keeps on repeating and can do left curves with negative angular velocity, right curves with positive angular velocity, or straight lines with zero angular velocity. But those are not safe under all circumstances, but they're only safe under some circumstances. So there's the question, if this is your Wall-E robot, do you happen to have a guess how you need to choose those various conditions? When is it safe to go left? When is it safe to go right? When is it safe to go straight? For the moment, when you use only a single velocity, a single obstacle on the area. Any guesses? For the straight part, what do you need to do? You basically need to look at the line and see if this line goes to the obstacle. Going straight might be a bad idea because this dynamics doesn't tell you how long you do it. Right? There's no time variable in it. There's no time lock that tells you only follow the differential equation for at most 10 seconds or so. You might be following this guy forever, right? So check the line, and if there's no obstacle, fine. And in similar ways, do you need to do the circles. Something that's rather cool, however, is that this is not just a practical device for doing proofs, and you saw them in exercise in Chimera X, where you can basically follow your nose, point at a bunch of facts, and do the proofs in the way that your intuition goes, which is something that's very important to me, and it's also very different compared to a previous generation theorem prover, just Chimera, where you were forced to always work on the top level of all the questions. And if you say, I already know what to do deep down in the middle of it, the old prover said, you follow on the my regime. And the new prover, you're the boss, so you can just point at facts and it will do the thing for you as you see fit. You can also just edit facts. And it appears as if you would be, in fact, maybe I should do that. Well, let me see. Let's just quickly get ourselves a new proof for the bouncing ball because we looked at it already. And then unfold and say run until you have an interesting question. The interesting question is a loop. It says, loop invariant. Yeah, it looks kind of good. Okay. Yeah. And then here, for example, if I want to, I can take this formula here and just edit it and say, I want a different formula here. Let's say I have a v square here that I don't like because it can't understand what's going on. I'll turn this into a plus on the left on the left-hand side. And then it accepted that change, but by having accepted it, Chimera X actually did a proof behind the scenes to show that the editing you've done in your formulas actually made sense and was a sound thing to do. This is a very intuitive, like notebook-style scratch proof. Or also suppose I am misplacing a formula. Suppose I hide this. Let's say I hide the fact that gravity is positive. Right? If we're in an anti-gravity field, bouncing balls work very differently. And if I now try to prove it, it won't work. In fact, let me do just that. Oh shit, this case was still fine. Let me do the same thing in another case. Okay. Let me try this one. Okay, now it has the effect that I wanted. It says, well, I could prove this if only false would be true. Yeah, okay, so that means I made a mistake somewhere. Of course, I know my mistake. I have hidden an important fact. Let me step back. Now I can say, I don't get this. Tell me a counterexample. Yeah? And then it says, well, here's a counterexample. If you plug in these numbers, it won't work or so. Yeah? Oh, there's also some simulation capabilities and some finding assumptions capabilities and all kinds of things for interacting with proofs. Good. But the point I was trying to make is that it's not just a useful tool, and a very simple one, actually. Just these 10 axioms, basically. Yeah? For doing proofs and doing actual proofs, but it is a theoretically good one because it has a sound and complete characterization. So it is indeed true that, first of all, it's sound, which is a conditio sine qua non for logic, so a condition without which logic wouldn't be. I wouldn't stand here and talk about it if I hadn't had a soundness proof for it. In fact, the soundness proof is so rigorous, as I mentioned, that it's also mechanized in Isabelle and also in the Hall, Isabelle Hall and in the Koch theorem prover. And it's also complete relative to differential equations, which means that proving hybrid systems actually is the same as proving continuous systems. And it's the same, shockingly, also as proving discrete systems. All you need to do is throw in those 10 axioms, for example. So you have a system, and it's complicated, but you identify, the most important part, what are its continuous pieces, which individually are simple, what are its discrete pieces, which individually are simple. This step is underestimated, but it's super important, getting the question right by using our human understanding of the system. You throw them back together into a hybrid system, which is still as complicated as the original one, but the benefit is that the individual pieces have gone reasonable. And then it turns out that even though these are all on very different footings, continuous signals compared to discrete signals, that the theory of continuous systems is proof theoretically identical to the theory of hybrid systems, is proof theoretically identical to the theory of discrete systems. They're all interreduce, and the proofs are constructive. So you can reduce every question about a continuous system into a question about discrete systems, and you can reduce every question about a discrete system into questions about continuous systems. And in fact, the way we really win is to answer every question discretely if that's natural for an answer, and answer every question where a continuous answer is more natural, answer that in a continuous style. Look at the Licks paper from a few years ago. Also for a relative decision procedure for it, for example, for, of course, only closed sentences. The Chimera X prover not only gives you, helps you in proof search by reducing model safety questions, but it also generates compliance monitors, which is also very important. Monitors that say, well, you have a beautiful safety result for the model of a car, but your actual car is a different question. Maybe you got the model wrong. Important question. Everybody stands at conference and says, I have verified a CPS. They're all lying. They all verified a model of a CPS. Yeah. With Modelplex, which is also implemented in Chimera X, we can bridge that gap and synthesize with a Modelplex tactic, which is just a push of a button, a monitor for you that will check at runtime of your actual car whether it happens to fit to the assumptions that your model has made, such that the proof that you've done about the model implies the safety of the actual system running at that moment, which is a super powerful mechanism. As I mentioned, the reason why it is so trustworthy is that it's based on a uniform substitution principle, which is sound complete and gives us a very small standards critical core in the system of just about 1,700 lines of code, which is actually pretty good. It's sort of programmable, all kinds of things, which is particularly good if you compare it to other provers and so on. For example, Chimera was our previous generation prover, which had 66,000 lines of standards critical code, and we now went down to just 2% of it. But it also compares quite well, with other theorem provers like He, New Perlmutter, Parole, Isabelle, Koch, and so on. We're doing quite well as far as that's concerned. Whole lot, of course, it's not invisible in the sense that it has no soundness critical core, but it's just so small. It's 400 lines of code, so it's about a fourth of what we do. But we also do have differential equations treated, and as part of that, a whole lot, of course, treats it something slightly different. But also, we're comparing quite well with other hybrid systems tools like Favor and HSolver and SpaceX and Flowstar and DReal. HiCreate. HiCreate has, of course, a certain part of the model analysis which is specific, and also on the sound critical part. So in a sense, I would always characterize HiCreate as sort of relatively sound, because if the user does the right thing as part of the analysis, the system will give you very awesome answers. Chimera X is sort of the opposite. It's always sound no matter what, and is relatively complete. So if things fail, then they fail because the proof wasn't found in finite time. But people will usually notice that. And the point is that You know, if people would like to be done with a safety analysis, there's no better time to ask them to believe anything as a proof than if they're in the middle of a complicated system design and they just want this thing to be over. Yeah? They'll say believe anything, which is why Chimera X is based on a very, very small standard critical core, and everything's bootstrapped from that. In case you're curious, uniform substitution is this proof rule. All it does is it says, if a formula is valid, so it has a proof, then a substitute of it is also valid. A substitute of it where I substitute, for example, formulas in for predicate symbols, or terms in for function symbols, or in fact also programs in for program constant symbols. Here's an example. If we have this fact, which we do because it's one of the axioms, the axiom of non-deterministic choice, not the axiom of choice, the axiom of non-deterministic choice. If we have a choice between A and B, then P is true, if and only if we have a choice of A and P is true, and after a choice of B, P is true. Because we have that, the uniform substitution says we also have a proof of this, that if I replace A by, for example, the discrete guy x is x plus 1, and if I replace B by, for example, the continuous guy x prime equals 1, and if I replace the predicate symbol P by, for example, the formula x squared equals 0, then this is also equivalent to that. And that's the reason why our prover core is so small. It doesn't know anything except it implements the uniform substitution proof rule. There's only one proof rule in the system, basically, plus renaming and a little bit of things just for efficiency reason, like and rules or so, which we don't really need, but it's convenient. And then a list of axioms. So extending and changing the system is very easy too. All you need to do is copy paste in a new axiom, and off you go. We've used it in a bunch of cases, lots of course to be precise, but some highlights are robot obstacle collision avoidance and ground navigation, train control braking systems with pressure brake propagation along the train, which is a little complicated because depending on how aggressively you do this and so on, and if you want to stay on the safe side, you have about 5,000 was it kilometers or feet? Either way, I keep forgetting the units. But a long safety margin distance, which you either have on the collision side or an unnecessary conservativeness. The next generation airborne collision avoidance system, which is going to fly hopefully soon, and some ship cooling systems. And of course, I want to acknowledge the sponsors and collaborators, which, if I understand, is a good place to stop. If you have any more questions at this moment, let me know. What I will be continuing after in the afternoon or so is what do we do with reasoning for non-elementary cyber-physical systems. I've shown you everything you need to know about elementary CPSs, the ones with solvable differential equations. But what happens with CPSs with more fancy ODEs is a topic for the afternoon. Thank you.